Alaikum. This is lecture number 3, Physics 281. Today we'll talk about the coupled oscillations. In the previous chapters, we discussed a single oscillator system. In this chapter, we will study coupled oscillation. Two oscillations share a common component such as stiffness S, capacitance C, inductance L, or mass M. Coupling of such parameters together allow for energy transfer and consumes no power. This is the basis of the wave motion. If two waves are able to transmit energy to each other, then these waves are said to be coupled. As a first example of the coupling motion, let us take two identical pendulums connected by a spring of spring constant K. If the system is set in motion, then we assume that the displacement of the right mass x and the displacement of the left mass y. Each mass subject to two forces, one from the spring, the other is the component of the gravity or its weight. Now the equation of motion for the right mass is mx double dot minus is equal minus k of x minus y minus mgx over L. We already have this term before. For the left mass, this is right mass and this is left mass. You have to correct this. My double dot equal minus k of y minus x minus mgy over L. The coupling is through this expression k of x minus y. Now, in order to solve these equations, these two coupled equations, we have to use this transformation x capital equal x small plus y small and y capital equal x minus y small. Then take the first derivative and the second derivative. Add the two equations 1 and 2 together and then subtract. Adding them gives mx capital dot minus k of x minus y. Adding them together gives m of x double dot plus y double dot equal minus mg over L of x plus y. X plus y is x capital, x double dot plus y double dot small is x double dot. So we have one equation x double dot plus g over Lx equal 0. We know this equation before. Now subtract the two equations, we get my double dot minus k minus mg over L times y. So we have now two coupled equations. We know what's the solution for each equation. The first equation has a frequency square equal g over L, which is the natural frequency of each pendulum. The second one has a frequency omega 2 equal square root g over L plus 2k over m. The solution for the first equation, x capital equal x0 cosine omega 1t plus phi 1. For the second y capital equal y0 cosine omega t plus phi 2. Now if y capital is 0, that's x minus y equals 0, then x equal y. Then the motion is described by the first equation, which is x double dot plus omega 1 square x equal 0 with the frequency square root g over L. In this case, the two pendulums are in phase. Now if x equals 0, if x capital equals 0, x equal minus 1, then the motion is described by the second equation, which is y double dot plus omega 2 square y equals 0. I'm assuming omega 2 greater than, it's actually omega 2 greater than omega 1. So the system now of the two pendulums are out of phase. If the right mass moves to the left, if the right mass moves to the left, the left mass moves to the right, and vice versa. Now we have to introduce the concept of normal coordinates, degrees of freedom, and normal modes of vibration. The normal coordinates are those coordinates that oscillates with a single frequency. The equation of motion contains only one dependent variable, x capital or y capital. Energy of the coupled motion is the sum of the squares of x capital, x square, x dot square, y capital, square, y dot square with some multiplied constant. We will discuss this later. Normal modes are independent of each other. Energy associated with a normal mode never exchange with another mode. Each independent mode is called degree of freedom. For the previous case, we have 2 degrees of freedom. Here again we have these two equations. We know that x capital X is x small plus y small, and y capital is x minus y small. The most general solution for x capital is x0 cosine omega 1t plus phi 1, y capital equal y0 cosine omega t plus phi 2. X0, y0, phi 1, phi 2 are determined from the initial conditions. Now assume that x0 equal y0 equal 2a and phi 1, phi 2 equals 0, then the two equations reduces to x capital equal 2a cosine omega 1t and y capital equal 2a cosine omega 2t. Now for x small, we have 1/2 of x capital plus y capital equal x small, which is a cosine omega 1t plus a cosine omega 2t. We have to add these two waves together. For y small, we have 1/2 of x capital minus y, which is a cosine omega 1t minus a cosine omega 2t. We have to add these two waves together. The velocities, just take the first derivative with time. Now, given by these two expressions, if at t equals 0, displaying the right mass by 2a, this is the right mass, and releasing both masses from the rest, then x capital equal 2a and y capital equal 0, x dot y dot at t equals 0 equals 0. The motion can be seen as a combination of two motions. For x capital, the two masses are in phase, or two waves are in phase, and for the y, it looks out of phase. This mass goes to the right, then this goes to the left, and vice versa, as I said before. Now, x small, for the right hand side, x small is a linear combination of these two waves, which can be written as 2a cosine delta omega over 2t cosine omega average over 2, where delta omega is omega 2 minus omega 1, and omega average is omega 1 plus omega 2. We met this equation before in chapter 1. There is an envelope here represented by 2a cosine delta omega over t, which is the amplitude of the wave, and this is the inside wave is cosine omega average t over 2. Similar things for the y small. Here we subtract the two equations, so we get 2a sine delta omega over 2 sine omega average t over t. We start from a sine wave. This is the envelope, the variation of the amplitude, and this is how the frequency varies. This is the sine omega t, sine omega average t over 2. Now, after release, the displacement okay, this is what we have today. Well, next time we will discuss the energy concept for such motion. Thank you.